Есть.
Сейчас у меня он еще не начался. Так, теперь это я убираю. Так. Так, ну все, теперь можно начинать. Окей, I may begin. So I would like to repeat my request to send me, please send me your addresses either on the chat or to my email address. My email address is here. I will use it for any kind of correspondence. I will send you problem sets, also the updated PDF of the notes, and I want also to receive any feedback. So please ask me questions. If you wish, we can ask me just in the course of my talk, or if you wish, we can write me an email and ask questions in your letter. I will try to answer. Okay. So my course is about representations of classical groups. So what are classical groups? So there are 4 infinite series of classical groups over the field of complex numbers. They are usually denoted as 4 series, A, B, C, D, A, B, C, D. Series A is the general linear groups. Series B is orthogonal groups of odd degree. Series C are the complex simplicity group, and series D is composed from orthogonal group of even degree. And each of these groups is a complex Lie group. And the finite dimensional representations, I mean complex analytic representations of these groups are the same as finite dimensional representations of the compact forms. These compact forms are the maximal compact subgroups. The series A, in series A, these are the unitary groups. In series B, compact orthogonal group, compact simplicity group, sometimes it is denoted as, okay, as some alternate notation in Hermann Weil book is this one. And series D is the compact orthogonal groups. So I will discuss representations later on, but I would like to start with their characters. The reason is that the characters determine these representations uniquely. So one can develop a large part of the theory on the level of characters. The characters depend on matrix eigenvalues, which means that they are class functions on the group. And so one can treat them as symmetric polynomials in n variables. N is the same as here. And I would like to concentrate first on these polynomials. So I will regard for some time characters for me will be simply some combinatorial objects, some symmetric polynomials. So I will start with the characters of in series A, that is the characters of the general linear groups. They are indexed by object, by combinatorial object. Which are called signatures. A signature of length n is an n-tuple lambda of integers which are weakly decreasing. I denote by in this way the set of all signatures, and I will often use this notation. Please look at it. And I would like to emphasize that these labels L1, Ln are strictly decreasing, while the coordinates of signatures are weakly decreasing only. The next notation I need is the conventional notation for the van der Monde determinant. It's here the product of all differences between these coordinates. And next, S of n is the symmetric group in n letters. It is viewed as the set of permutations of some collection of n letters. Now the definition of series A irreducible characters. First of all, they are indexed by arbitrary signatures of length n. So choose some collection of n coordinates u1, un, which may be viewed either as complex variables or possibly as simply formal variables. And given a signature lambda, we set this definition. This is the definition of some rational function. Here is the determinant of order n, and divided also, in fact, by a determinant of order n, which is the van der Monde. Okay. And here, in the numerator, I already use these labels, these shifted labels L, which are attached to the coordinates of lambda. And these are indeed, this will be seen later, the irreducible characters of GLN. For instance, this is some simplest example. For n equal to 1, these are simply Laurent monomials. For n equal to, the characters are given by this formula. And from this formula, it's already seen that these rational functions are indeed Laurent polynomials, because the numerator can be divided by the denominator. Okay. Are there any questions, please? Okay, is it clear? Perhaps some people know all this matter quite well, but later on we will see some more sophisticated, one can say so.
Sorry, could you please show again the definition of the character?
Okay, sorry. So this one. Okay. So this is the numerator. These are the variables, and raised in powers L, and these powers are the shifted coordinates of the lambdas. Okay.
Okay, thank you.
Okay, let's go further. So some first properties. Property 1. These are symmetric Laurent polynomials. Now, symmetry is obvious because we have a ratio of two skew-symmetric objects. So the ratio is a symmetric object. Next, they form a linear basis of the algebra of symmetric Laurent polynomials. Okay. Even more, these objects are indeed defined over Z, the ring of integers. So one can deal with Laurent polynomials defined over the base ring Z. Next, property 4. What happens if you invert the variables. The result is some transformation of a label lambda. Lambda star is obtained by writing the coordinates in the reverse order and adding the minus sign. Okay, so they are again weakly decreasing after this transformation. The next property, which is quite trivial from the very definition, but it's very important indeed, is the following. Assume that we add to any coordinate some constant k, an integer, and the result is the characters is simply multiplied by some power of a product of the coordinates. Okay? How to prove this? There are essentially two non-trivial but not very difficult claims. First is lemma is follows. Take any commutative unital ring, but for I think it's work of a field of characteristic P, but let's assume to be safe that the characteristic is zero. So in principle, one can take Z or R or C, what we want. Then look at the operator of multiplication by the van der Monde. So this is the operation which transform F to F multiplied by V. And they claim that this is a K-linear isomorphism. This is an isomorphism not of rings, but of linear vector linear spaces between symmetrical Laurent polynomials to skew symmetrical Laurent polynomials. Okay? So from this transformation, one can say that we can identify these two linear spaces. But in the space of skew symmetric Laurent polynomials, there is a very natural basis. These determinants, or in Hermann Weyl terminology, alternants. So we simply take a monomial which is indexed by the L's and anti-symmetrize it. This is the simplest possible basis in skew symmetric Laurent polynomials. Okay? So the claim is that this is a basis even over Z, for instance. The basis in the ring of skew symmetric Laurent polynomials. And using this to claim, which are some exercise to prove, using this to claim, we can prove all the claims from this proposition. So this is trivial, of course, this is trivial, but the first two claims are less trivial. So the main idea is that any skew symmetric, I would like to repeat, any skew symmetric polynomial can be divided by van der Monde. So this is very important because, and I would like to emphasize that this works only infinitely in the case of finitely many variables, because the van der Monde exists in finitely many variables in this case only. So later on, we will work with the algebra of symmetric functions with infinitely many variables. So we will need some procedure of truncation, of reducing to the case of finitely many variables. Okay, the next topic, also very important, is orthogonality.
Can I ask one quick question about the
Okay.
notation? When you said when you define the character, use chi superscript A, what's that A?
Sorry, excuse me, I did not understand. Repeat, please.
When you used when you define the character, you used chi superscript A. I mean, what's that A? Is that only for the A?
A, what is A?
Yeah.
I'm sorry, A is the label of a series.
So you are only defining
series A.
So you are only defining it for the series A, or?
Yeah, A, yes, yes.
Okay.
only for series A. The series B, C, D will appear later, not today. Okay, thank you.
Григорий Иосифович.
Да.
Григорий Иосифович, а
Да.
эти, простите, пожалуйста, а эти записки будут куда-нибудь выложены?
Может быть, будут выложены, но я, поскольку они будут дополняться, так сказать, меняться, то я их буду просто по мере обновления буду посылать по электронной почте участникам.
Ага, спасибо большое.
Потому что выкладывать их сразу, это, у меня нет прямого доступа к сайту, скажем, Skalltech. Но, может быть, я их буду выкладывать на мою страничку в институте, в EP. Ну, посмотрим. Ну, я думаю, что проще посылать их.
Спасибо большое.
И это, вот
А
это
возможно
еще
их выкладывать?
одна причина, почему я прошу прислать мне email. Да? Sorry? Any
Я
question?
говорю, может их выкладывать до лекции? Говорю, до лекции может их выкладывать, чтобы людям было удобно во время лекции, если что, там на страничку вперед, назад.
Ну, посмотрим. Может быть, да, посмотрим. Ну, пока давайте так, а там будет видно. Может быть и так. Вы правы, я посмотрю, как пойдет. Я пока еще не знаю, как быстро я буду двигаться, там будет видно. Okay, so I return to orthogonality on the torus. So let T be the unit circle, and I need the uniform measure on the unit circle. So theta is a coordinate, and this coordinate, the measure takes this form. And consider the Hilbert space of complex valued functions on the torus, which are invariant under permutation, so simply symmetric functions. And the inner product is given by this formula. So this is, we take the inner product with respect to a weighted measure. The weight is the squared Vandermonde, the modulus of a squared Vandermonde. Okay. So this is the inner product, and this constant is also important. Now the claim, which is a very useful exercise. So the characters form an orthonormal basis in this Hilbert space. So here there are essentially two claims. One says that the characters are orthonormal, so they are orthogonal and have a norm equal to 1. And the second claim that they are total, which means that their span is dense in the Hilbert space. So this is a true basis in the sense of Hilbert spaces. Okay. So the next claim that the characters can be characterized as the only up to sign plus minus symmetric functions on the torus, which are have integral Fourier coefficients first and norm 1. So this is a very important claim because it is just the core of Hermann Weyl's approach to the classification of the characters. There are essentially two approaches to classification of characters of compact Lie groups. One is, one can say, is integral or global approach, which is due to Hermann Weyl. Another is some purely algebraic approach. But for the integral approach, which is the original approach of Weyl, this is just the key argument. And I would like to mention also that this property is also very close to some property of characters of symmetry groups. So Hermann Weyl approach in his book on classical, in his book of classical groups, is very similar to the original Frobenius approach for the classification of the irreducible characters of symmetric group. If you compare the exposition in Hermann Weyl's book and say the exposition of MacDonald of Frobenius, or one can also look at the original paper by Frobenius, it's very readable. You will see that they are very similar in some aspect, they are very similar. The next property is also very, very important, is the so-called principal Q specialization. So I would like to jump first to this property, to this corollary, which is the file dimension formula. So what is this quantity on the left-hand side? Actually, it is the dimension of the corresponding representation. I did not define representation, but we will see that this is just the dimension. How to obtain some formula, how to derive it from the initial formula, the ratio of two determinants. It's a bit difficult because if you substitute only the 1, 1, 1, we obtain an indeterminacy of type 0 by 0. How to resolve it? It's not evident, but a nice trick is as follows. Take the so-called Q specialization, 1Q, Q squared, and so on, a geometric progression. Then typically this number are distinct, pairwise distinct. One can take a formula, and a magic fact appears. One can just look at it a bit closely, and you will see that the result of this substitution leads to the ratio of two Vandermonde determinants. So you get in this way a closed expression, and from it is easy already to pass to the limit as q goes to 1 and get this beautiful formula for the characters. Okay, so what is next? Now I would like to discuss a little bit symmetric polynomials, not Laurent polynomials, but ordinary polynomials, and essentially the Schur polynomials. So just some preliminaries. So this is my notation. This is the algebra of symmetric polynomials in n variables, say over the reals or over complex fields, does not matter. I need the elementary symmetric polynomials. By agreement, the polynomials with index 0 is equal to 1. They are given by this formula. Okay. So this is a well-known object. There is a natural generating series, this one. It's a polynomial. Next, there are very similar objects, which are called complete homogeneous polynomials. This is their definition. And look, the definition is very similar, almost the same. The only difference that here we have strict inequalities, and here the indices are subject to weak inequality. But the result is very different. We get quite different objects. The generating series is as follows. This is a simple exercise. Probably you know this. And there are the claim that the algebra of symmetric polynomials in n variables is freely generated by the first n elementary symmetric polynomials, or equally well by first n complete homogeneous polynomials. This is not too trivial, but not too difficult to prove. So I would like to propose you to prove this independently, or if you wish, we can look at any textbook. No, it does not matter, but I would like you to do this exercise. Okay, so the next topic is the so-called positive signatures and Young diagrams. So the definition. By a positive signature, I mean signature with non-negative coordinates, non-negative coordinates. I call them positive signatures. So this is my notation, This is my notation for Young diagrams with at most n rows, non-trivial rows. Okay? And there is a natural way to identify the positive signatures of length n with this set of Young diagrams. So we can, the idea is just, okay, so the idea is as follows, so we can just draw some picture like this. This is a Young diagram. And if the number of rows is less or equal to n, we can regard this as a signature, some number of boxes, some number of boxes, and some zeros, which are added if necessary. Now the Schur polynomials. Schur polynomials. So the definition is as follows. The Schur polynomials with n variables is a particular case of a character. So the Schur polynomials are series A characters with non-negative coordinates. And they are labeled, it is convenient to regard them as indexed by Young diagrams. So this is just a definition. So they are ordinary polynomials and not Laurent polynomials. And maybe you can ask, we can think of this as some trivial fact, but it's actually it's important. The idea, some I could say informal idea, is to think of the x's as additive variables, in contrast to multiplicative variables u, which are used in the definition of general characters.
Sorry, what means additive variables or multiplicative?
Just take this as some informal remark. It will be maybe more clear later on.
Okay.
Some informal remark. So the next claim is the Schur polynomial. The Schur polynomials, which is my notation as lambda, form a basis of the ring of symmetric polynomials, ordinary polynomials, not Laurent polynomials. And they also form a topological basis of the ring of symmetric power series. What means topological? Which means that any symmetric power series can be expanded on the Schur polynomials, and this expansion is unique. And actually, this holds even over the base ring Z. Okay? Sometimes it's convenient. It's important to use the base ring Z and not a field. Now, the claim is as follows, which is, this claim is easy from the very definition. So the first claim is if you substitute, if you specialize the last variable to 0, then the result is either the similar polynomials in n-1 variables, if the length is strictly less than n, so the last coordinate is not lost. In this case, we get the similar polynomials. Otherwise, we get 0. Okay. Again, I repeat, it's easy. But this is not easy, not completely easy. And the Crochet identity, which I will discuss now, is, I think, maybe the most important identity of a symmetric, of the theory of symmetric functions. Because there are many versions of a Crochet identity, I will discuss now only its simplest form, which is related to the Schur polynomials, but there are many more involved versions of a Crochet identity, which are related to McDonald polynomials and even more and more complicated objects, and they play crucial roles in many constructions. So it's important. So the Crochet identity for the Schur polynomials is the following identity. On the left, we have an infinite sum over all Young diagrams with at most n rows. On the right, we have a very simple expression, this one. And this identity is understood as the one in the ring of formal power series in 2 times n variables, the x's and the y's. How to prove this? This is, I would like to indicate the idea for the reason that it is also a very useful trick. A very useful trick. I learned it from some Japanese colleagues. I think these are Ishikawa and Wakayama. But probably other people know it also from some other source, but okay. So let's define 2 matrices, A and B. In these matrices, the rows are labeled by indices k ranging from 1 to n. But there are infinitely many columns which are labeled by the indices I, which are non-negative integers. And the entries are as follows. We simply take our variables and raise them in power n, here and here. Is it here? Okay. Okay. But a little idea, it is very convenient to arrange these indices. Oh, sorry, it's not I. This is, so this is not I, but n. N in the reverse order. We have to read them from right to left. It's convenient. So this is my matrix A. This is my matrix B. Okay. Now let's B prime be the transposed matrix. Then we can define the product of these 2 matrices. And this is already a finite order matrix of order n by n. These are rectangular objects, and after this transposition, we get a finite order matrix. And the entries of this matrix are computed easily, okay? And they are as follows, okay? The determinant of this matrix C, of this matrix, is the Cauchy determinant. This is an elementary exercise in algebra. How to compute this determinant? The answer is here. So this is also known as Cauchy lemma in Hermann Weill's book. It's a very nice exercise. I hope you know it. But on the other hand, the same determinant can be computed in another way, just from this formula, by using the Cauchy-Binet identity. What says the Cauchy-Binet identity? The determinant can be obtained as an infinite sum of product of 2 minors. And these minors, these submatrices, are obtained just by extracting from A and from B the columns labeled by L1, Ln. So this is here, the n order submatrices with these columns. But these objects are just the numerators in the Hermann-Weyl formula. So doing this and then dividing by the product of the Vandermonts, we get the desired identity. Okay. The first corollary. These homogeneous polynomials are nothing else than the one-row Schur polynomials. How to obtain this? Hint is as follows. Specialize all the y variables to 0, except the first one. What happens? Look at this property. Okay. If you specialize the variables to 0, okay, only polynomials with some special properties on lambda survive. If all by the first variable are sent to 0, only the one-row polynomials survive. Okay. So this is the hint why we get this identity, this equality. But this is trivial. But the next claim is not trivial. It is the so-called Jacobi-Trudi formula or Jacobi-Trudi identity. It looks as follows. It allows us to express the Schur polynomials as the single determinant in the H polynomials. This is the formula, okay, with the understanding that the H functions with negative indices are by definition equal to 0. This is important. So this is a simple example which shows what happens. 3 variables, we put on the diagonal the h's with just the coordinates, lambda 1, lambda 2, lambda 3. On the right, these indices increase by 1, by 2, and so on. On the left, if you move on the left, they decrease by 1 and so on. So this is the structure of this formula. Okay. I would like to explain how to prove this. Of course, we can find the proof in textbooks. For instance, in MacDonald, I forgot what kind of argument he uses, but I like very much some trick which I call some general recipe. It's as follows. Suppose we have some symmetric power series in the variables y's. We know that we can expand it on the Schur polynomials. So we can write such an expansion. And we are interested in the coefficients, how to extract some coefficients with a given label lambda. Lambda is given, how to find this coefficient. The answer is the follows. The corresponding coefficients is given by this formula. What this means? This is some conventional notation from combinatorics, which means we have some expression, and we have to extract the coefficient of some prescribed coefficients. Okay, so in this situation, this notation means take our function, our series, multiply it by the Vandermont, okay, and we get some other power series, some power series which is skew symmetric, and extract from it the coefficient of this monomial. This monomial is as follows. This monomial corresponds to the lambdas which are shifted, the L's actually. So the coefficient of this particular monomials just gives us these coefficients. Okay, this is an easy exercise, but it's very important because it works in many situations. Now we can prove the Crochet identity. So I repeat this definition. So the idea is to regard all the x's and all stuff which related to the x's as coefficients. Okay? But the variables are the y's here. Okay? So we regard both sides as symmetric power series with respect to the variables y. And more formally, if you wish, this means that we are working with the algebra of symmetric power series over the ring K, which is the ring of symmetric polynomials in the axis. Okay? So take as F the right-hand side, but write it as the product of generating series of H functions in the axis. And the y's are now the variables in the generating series. Okay? And use our recipe. So what we have to do, just take the shifted coordinates, okay? And look, and we know that our desired polynomials, short polynomials, can be obtained by taking the coefficients of this monomial in this expression. Okay? So what is this expression? Just look at it. This is the van der Monde. It's here. And I replace F by the product of the generating series. So it's 3, okay? So what is here? I'm sorry, this is some error. This is just the same. Just the same. Okay, sorry. So what is here? I replace this symbol by the true determinant. I regard this not as a product of differences by a determinant. Okay, so it's here. The next transformation is as follows. I introduce the h's inside the determinant. Okay, so I get this expression. Okay? But now I can use this term and also introduce it inside the determinant. This means that I have to extract the needed coefficients inside the determinant. But what is written here? Look, please look at this. I claim that if we want to get this power, and we already have this monomial, we just take some necessary term from here. And this necessary term is this one. So this is the result. Okay? And in this way, we get the entries of the Jacobi-Trudi formula. Now I would like to explain how to obtain the second Hermann-Weyl formula for general characters, not for short polynomials, but for general characters in series A. So we return to the general characters, which are indexed by arbitrary signatures. Okay, so now lambda is an arbitrary signature with possibly negative coordinates. So these are Laurent polynomials, not ordinary polynomials. But what are the H polynomials? And it turns out that here we have two kinds of H polynomials. The ordinary H polynomials here, and their relatives, which are obtained by inverting the coordinates. This is because we have to give equal rights to positive powers and to negative powers. I denote this Laurent polynomials with the star superscript. Okay. Again, we agree that the polynomials with index 0 are simply the constants 1. Okay. Also, we agree that polynomials with negative indices are by definition equal to 0. So the problem I would like to discuss is to express our characters through these h functions and h star functions. The next idea is to write a signature as a pair of Young diagrams. This is very easy, but I will explain this. For some reasons, people usually do not use this notation in many textbooks. Some people use it, but many textbooks do not pay attention on this possibility. So any signature can be indexed by a pair of Young diagrams, say mu and nu, with subject to this restriction. The sum of the lengths of mu and nu should not exceed capital N. So this is the picture. Okay. So mu is responsible for positive coordinates, mu is responsible for the negative coordinates, and inside we can add some number of zeros if necessary. Maybe I would like to write some picture. I like to write something like this. Okay, so these are a Young diagram which is responsible to mu and something like this. This is nu. So how to read this picture? We just count the number of boxes. The first coordinate, the next, and so on. These are possible zeros and negative coordinates, which are obtained from. Okay, so this is a very nice picture. And please keep it in mind. And now the second while formula. First, the statement. So let lambda be a general signature and write it as a pair of two Young diagrams. Next, choose some decomposition of n as p plus q, satisfying this restriction. It's typically, it's not unique, but take any one. Okay. So the claim is that one can write our character as a determinant of some matrix L. I will explain a bit shortly what is this L. And this L is n by n matrix, which is composed from the functions h and h stars, and which generalizes the Jacobi-Trudi matrix. Okay. So this is an example. So assume p is equal to 3, q is equal to 2, and just to simplify the notation, let's abbreviate. This is the symbol just means the h function with index n, and this symbol likewise means the h star function. Then the matrix L is something like this. So what is the structure? On the diagonal, we put first the indices corresponding just to the coordinates of mu. Okay? And here we put the nu, but written in the reverse order. Okay? So let's divide the matrices into parts. The part corresponding to the mu is obtained as follows. Complete the picture using the rule that the indices increase step by step to the right, from left to right, from left to right. And here, just in the opposite direction, from right to left, from right to left, from right to left, okay? So this is some blank space. I would like just to try to write this again. So this is something like this. Here are the new. And we go up. And here we go in this direction. So we have to write mu1 plus 1, mu2 plus 1, and so on. And here mu1 minus 1, so on. So here the indices increase from left to right. And here they increase from right to left. So here we write plus 1 star. So in this way, we get a matrix. So it can be divided into parts. Here we have P rows, and here you have Q rows. Okay. So remark that if Q is equal to 0, so in the polynomial case, we just get this picture. We just get this picture, this one.
So we assume that there are no zeros here, yes?
No, no. The reason if Q is equal to 0, this part on the left of this line collapses. Okay, because this is Q. If Q is equal to 0, only this corner exists. Okay. All these blocks disappear if Q is equal to 0. Okay.
I'm sorry.
Do you understand? I would like just to repeat what I would like to say. I would like to say that we have, sorry, it's not. So we have a block matrix, okay, in general. But if Q is equal to 0, only this block survives. And this block looks exactly as in the case of Jacobi-Trudi. So this is a generalization of a Jacobi-Trudi matrix, but it's a bit more complicated. Is it clear or not? Should I repeat maybe?
I have a question.
Okay.
So if in lambda there are zeros, we put them in P or in Q?
No matter.
Григорий Васильевич, а можно, пожалуйста, пример выше показать еще раз для частного случая?
Пожалуйста.
Спасибо большое.
No matter, Ira. You can choose any partition. You can choose.
But matrix will be different.
But the result will be the same. With agreement that negative coordinates produce zeros. So this some remark I would like to explain now. So the first Hermann-Weyl formula, it refers to the ratio of two determinant expressions. So do you remember the ratio of one determinant divided by the van der Monde determinant? Okay, this is the first Hermann-Weyl formula, it makes sense in general for any simple algebras, semi-simple or reductively algebras. But the second while character formula refers to a single determinant expression involving the H functions. It makes sense, I think, for classical groups, classical Lie algebra. But there is some little mystery. I would like to explain it. While derived his second formula for the orthogonal character, for symplectic characters, which is a non-trivial result, I think, that is for the series BCD. But for the series A, he restricted himself only with the Jacobi-Trudi formula, which is responsible for polynomial characters only. So why? So why? I repeat, it's a mystery. It's a good problem maybe to pose to historians of mathematics. I think it would be absolutely absurd to think that Weil was unable to derive the second formula for the series A in full generality. So why he did not write it? So a possible explanation for me is that he simply did not think it's necessary. For the reason, in series A, a general Laurent character can be reduced to a polynomial character with the help of multiplication by a suitable power, which kills negative powers of the variables. I'm sorry, I would like just show you the formula in the very beginning, just to attract your attention to it. Sorry. This one, you see? By using this multiplication, we are able to kill all the negative coordinates and reduce the problem to polynomial characters, that is, to sure polynomials. So this is possibly the reason why I did not consider this more general second character formula. Okay. But it turns out that for some problems it's good. This trick of multiplication by this expression is good. But for some problems, this viewpoint is unsatisfactory. For instance, for me, it was absolutely obvious because I worked with some analysis of representations for infinite dimensional groups. And for infinite dimensional classical groups, it appears absolutely obvious that we have to give equal rights to positive and to negative powers. And these tricks in this situation becomes unnatural. Okay? But another negative effect of Hermann Weil's viewpoint is that for a long time, people seem to be unaware of the existence of the so-called Wald-Brouwer algebra. We will probably discuss it later. This object appeared in the works of Koike and Turaev only after 50 years after the publication of Hermann Weil's book, and even more after the publication of Brouwer paper. So I proceed now to some proof of a general second character formula. It is based on a very nice identity, which is one of the so-called Littlewood formula. Littlewood is not the Littlewood from Hardy Littlewood. He's another Littlewood, Dudley Littlewood. So keep it in mind, this is another person. So this is some generalization of the Crochet identity. So assume our n is represented as the sum of two integers, of two non-negative integers. So let mu ranges over the set of Young diagrams with at most p rows. Mu is defined similarly with q, and represent lambda as the pair consisted of these two objects, mu and mu. The formula is as follows. So what is the difference? The difference is that you have here two Schur polynomials. So there are three factors, not two factors as in the case of the Crochet formula, but you should view this as some single object, which is responsible in some sense, let's say, additive coordinates informally. And the right-hand side is also a little bit more involved because we have to take into consideration also the negative powers. Okay, so the x's are related to the positive coordinates, positive powers, and the y's are related to the negative powers of our variables. Okay, so this is some kind of Crochet identity. There are also similar formulas which are related to the orthogonal groups and simplicity group. I hope I will discuss this later on. So assume we know this formula, how to use it to derive the theorem. So the idea is follows. Look at this expression. Okay. So we want to express to find these coefficients. Okay, to extract it from this right-hand side and use the same recipe. So we have to take the right-hand side, regardless. It's correct because there are no negative powers in x's and y's. This is maybe one reason why I call they additive variables. They are not subject to inversion. Okay? And we have to extract the coefficient corresponding to the product of these two S polynomials. So the general recipe says that we can replace the Schur functions simply by monomials, these monomials, but for this we have to modify the right-hand side. We have to multiply it by the product of two Vandermonts. Okay? So just the same play as before. So here I recall what is this shorthand notation. It is these monomials. Look at it. Okay. So this is the x is raised to the mu powers, but shifted. Okay. Shifted powers. And likewise for the y's. Okay. And let's transform further. Okay. So the same play. Okay. Represent it as the product of the H series. Here we have a right-hand side multiplied by, and these factors come from the denominator. Okay, this gives us the H functions associated to the x's, and these factors produces these factors. But the next step is to write this product as a single determinant of a big matrix of order n by n. And to do this, how to do this? Just transform this quantity, this product, extract the y's, we get the product of the inverse y's with the x's. and together with this product, this gives us the Vandermonde in these variables. Okay, the Vandermonde, and then we can introduce this factor inside the Vandermonde matrix. Some little play. And after that, the same argument as before, which is used in the Jacobi-Trudi formula. So the next step is how to prove the Littlewood formula. And we use the same idea, but more complicated. We consider two matrices, A and B, as before. The rows are labeled by the integers from 1 to n, and recall that n is the sum of p and q. And columns are labeled by all the integers, which are written again in the reverse order, okay, from right to left. Okay. So this is the matrix A. Okay. And these commas are used to separate the zero, the columns number 0 and the column number 1. Okay, so 0 is on the left here and -1 is here. Okay, column number -1 is here. Okay, they just correspond to the powers, okay, of these variables. So the structure of the matrix A is very simple. Okay, this matrix is just composed from all the monomials in the variables u1 and u up to un. Okay, so it's very simple. The structure of the matrix B is more complicated. Okay, so we have to write the axis in this way. So again, remind that the axis can be raised only to non-negative powers, and also the y's also. So this is the picture, how to do, what to do. And we get another matrix, okay? So here we have P rows, and here we have Q rows. If I'm not mistaken, is correct. Now again, we take the product of A and B is transposed, okay, in two ways. First of all, we just consider the entries of this product, and they are given by some formulas depending on the on I. Where is I? Is it here or here? So see here, the difference is here. Two different formulas. And in this way, we get some expression like this. I will send you the file so we can look more closely on this transformation. And these are obtained from this formula. This is just another notation from the concatenation of the x's inversed and the y's. And the determinant on the right-hand side here is easily computed because it is reduced to the Cauchy determinant. Okay. After some simple transformation, we obtained such a formula. But on the other hand, use the Cauchy-Binet formula. Okay, so write again the Cauchy-Binet. It gives us this expression, similar to what we have in the case of ordinary Jacobi-Trudi. Only the matrices are more complicated. And looking closely on the form of a matrix B, it appears that the determinant vanishes. So the sum over all collections of strictly decreasing numbers, okay, with no restriction on the sign. They can be positive or negative, no matter. But now we see that from the structure of this matrix, it appears that the determinant, this one, vanishes unless we have this restriction and this restriction. And then we can write this collection as the sum of these two vectors, which is essentially the row, what I denoted by row, but with some a little bit modified. Okay. And mu and nu are Young diagrams subject to these restrictions. And we have this and this. And so we get another expression for this determinant. And comparing this formula and this one, we get, in this way, we get the second Weil formula. Okay. So this is the end. I did not think that I will be able to talk about all this stuff. So if you wish, we can ask some questions, please, if necessary. Are there any questions? So I understand it's not very easy to follow all these computations from this exposition, but I will send you the file. So you will read it, and maybe I hope it will be more or less clear, but if not, please send me email, I will explain it. So the plan for the next lecture is to, I think I will discuss what happens for orthogonal asymplectic characters. First the definition, then the second Weil formula. And then it depends. We can discuss, maybe we can discuss some stuff already related to representations. One possible topic is the materialization of these Cauchy identities, because each of these Cauchy identity expresses some fact from representation theory. It's not only some formal combinatorial formula, but behind it there is some claim about representations. In the case of ordinary Cauchy identity, this claim is related to finite dimensional representations, but in the case of the second, in the context of a second Weil formula, it's related to some infinite dimensional representations, the so-called highest weight but infinite dimensional representation. And I hope we can discuss all this later. So that's all. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Okay, so I can leave or no questions, okay?
May I ask one question? Я пропустил начало, извините.
Да,
А
пожалуйста.
были какие-то задачки, которые можно решать как-то, ну, или, ну, в общем, какие
Да,
будут?
будут задачи, я буду посылать задачи. Честно говоря, я еще их не составил. Вот, ну, как бы первая задача – это как бы проследить за вот всеми, так сказать, манипуляциями, которые я тут делал, потому что мне не хотелось как бы уж очень-очень медленно двигаться и растолковывать как бы все шаги. И потом это, по-моему, тяжело вот так со слуха воспринимать. Но для меня, например, это было бы тяжело.
Ну, это правильно проделать это самому, наверное.
А стоит это проделать, да, стоит проделать. Так что, так сказать, мой первый призыв – это просто вот я пришлю файл, вот, и на e-mail проделайте вот эти упражнения, просто восстановите все, так сказать, пропущенные шаги. Вот. А потом я буду давать еще задачи, конечно, другого рода тоже.
Хорошо, понятно. А как-то эти задачи просто мы сами будем решать, или можно будет как-то их кому-то сдавать, там, как-то?
Ну, вы знаете, тут есть как бы два аспекта. Один аспект – это формальный аспект, что нужно будет как-то, так сказать, проверять, как говорится, знания студентов, вот и давать какие-то задачи, потом, значит, их оценивать. Ну, это тоже будет, конечно, но, честно я вам скажу, я не буду очень сильно напирать на этот аспект. Мне хотелось бы, в общем, люди взрослые, вот, и я рассчитываю на активную, так сказать, сознательную работу. Вот, я буду стараться, наверное, давать еще много разных задач, ну, постараюсь во всяком случае, но буду разделять эти два аспекта. Формальный аспект, то, что там нужно для получения, так сказать, оценки, вот, и неформальный аспект, это вот людям хочется, так сказать, что-то усвоить.
Ну да, ну просто даже для неформального аспекта полезно давать задачи.
Конечно, я буду давать задачи, да, задачи будут, это
Хорошо,
я тоже
спасибо.
постараюсь, да, безусловно.
Ладно, спасибо.
Да, хорошо, все, тогда я прощаюсь. До свидания,
свидания.
тогда я прекращаю. Этот самый надо
свидания.
выключить. Да, до свидания.
Григорий